This is the third part of the terminology and vocabulary from dynamics unit, and we're going to focus on Newton's laws of motion. You've heard these before, probably in middle school, but we're going to iron out a lot of the confusions that often accompany the just memorizing what the laws are, because you really need to know how to apply them. So there were, in order for you to understand this better, you should know a little bit of historical background. So for many thousands of years, Aristotle was the leader of this thinking. He was from the 5th century BC, I believe. The natural state of things was to either be at rest, fall down, or rise up. And it was based on, the fact that things were either earth, air, water, fire, and things just went back to their natural place. So heavy things fell down because they were earth. Lighter things rose up because they were air, like that. Galileo, who worked in like the 1500s, like 2,000 years later, he came up with the idea that forces are not necessary to maintain motion. And he had this really elegant thought experiment that he did with a ramp. And you should probably look that up. Galileo's ramp, it's called. And to see how he thought this through, because he didn't do any experimentation. He just thought things through. But in the 1700s, Newton came up with the idea. He took these ideas, he did a lot of reading, and he put these things together, and he built on what Galileo said. And he said, not only are forces not necessary to maintain motion, but forces cause objects to accelerate. Isaac Newton was a really interesting character, and I highly recommend that you pick up a biography or even just read a synopsis of his life. We don't have enough time to get into it right now, but here is a little bit of an overview of his life. You can see how prestigious his degrees were, his education. He lived through some really tumultuous times in England in terms of the Black Plague, and he had a kind of difficult family life, and he remained kind of a recluse, except that there was a great renaissance in scientific thinking at the time, and there was all of these scientists created this community that pulled him into it. Robert Hooke especially was a great friend of Newton, and he really helped Newton become involved in this community and pulled him into the Royal Society of London to the extent that he was the president of it. But this was really because his friends and colleagues respected his thinking. It was really interesting. But I highly recommend you read the book Clockwork Universe. It's really good and gives you a very good insight in a historical fiction type of approach. So into the law. So the first law of motion was built upon Galileo's thinking. He just restated it. An object at rest stays at rest, and an object in motion will stay in motion at constant speed in a straight line, unless an unbalanced force acts on it. And one of the things that I am concerned with is that you know this by heart, but this piece is the piece that most people ignore. You see that? Okay, make sure when you learn this, right, it's fine to memorize it. Make sure you don't forget this part. At constant speed in a straight line. But better ways to state Newton's first law of motion that might have more meaning are any of these four. When net force is zero, an object's in a state of equilibrium. An object will continue its state of motion unless it's forced to do otherwise. An object cannot accelerate unless an unbalanced force acts on it. Or lastly, when forces are balanced, an object has zero acceleration. These are four ways of saying the same thing, as we said in the previous slide. Choose one of these that you like and the best, and that has some meaning to you, so that you can better understand this more formal statement. Newton's second law says that an object acted upon by an unbalanced force will accelerate in the direction of the force. This is more of an interpretation, an easier way to have understanding. Most people simply know the equation. They go, oh, Newton's second law, it's F equals ma. But the equation is a representation of the law, not the other way around. So you need to know what it means, not just what the equation is. So here's the equation. Often it's written acceleration equals net force over mass. So don't be surprised if you see it written this way. Okay. Third law of motion is well known as every action has an equal and opposite reaction, but most people have no idea what this means. So here's a much better way of, excuse me, a much better way to know it. Every interaction, we defined interaction in the first set of these slides, videos. We defined interaction in video guide 1, so you may need to go back to your vocabulary. So every interaction creates a pair of forces that are equal in size and point in opposite directions. This says the same thing as this, but this actually has meaning. This doesn't have meaning. Even if you know it well, you have to know it in a way that you can use it. So why do you need to know Newton's third law? Well, Newton's third law helps to define what happens when two things interact. Newton's second law helps to define when one object is acted upon by multiple external forces. So I want you to know the distinction between them, because most people apply these laws incorrectly because they mix up when it's appropriate to use one versus the other. So with second law, forces on the system are equal and opposite only when acceleration is 0. But for third law, action and reaction force pairs are always equal in size and opposite in direction. So you have to know how to identify action-reaction force pairs, which we will do in the guided practice. Forces are caused by different interactions, but forces are caused by the same interaction for the third law. And for the second law, we're going to learn how to draw free body diagrams, which show all the forces acting on a single system. But for third law, any action-reaction force pair, each of those forces has to be on a separate free body diagram because it's on two different systems.